Quat's recording it too.
Okay, yeah.
You good? Is there anything you need from me?
Yeah, I think that should be good. Thank you so much.
Okay. You know where I am.
Yeah. Okay, hi, I'm Jasmine. You can also call me Supercoder79, and I'd like to present some work that I've been doing over the last 6 months or so about Worldgen optimization and going the extra mile. It's working. Okay. Yeah, so as for a little background, I wrote a custom world generator for the Minecraft server Origin Realms. It's slightly different from conventional world generators because it generates an entire region file at a single time, and it's kind of divorced from Minecraft, so it's all standalone, so it doesn't depend on Minecraft code. But it does face the same problem that other large scale world generators face, which is speed, because you want your world generator to be fast because it's generally good. So just for a little context, before optimization happened, it took approximately 8 seconds to generate a region, approximately 120 chunks per second, which is pretty good. But so the structure of Origin Realms, there's a bunch of resource worlds that people can go and dig up and tear down and grab whatever they need. And there's 4 of them. So it cycles through a resource world every day. Well, it cycles through all 4 of them every day. So it needs to pre-generate 4 of them every day, which is an issue if it takes 2 hours to generate a 15,000 by 15,000 sized world, which is 900 region files. Because that takes 2 hours per file, per world, so that's 8 hours of pre-generating each day, not including the nether. So that was the main impetus to do this optimization. Yeah, there we go. So after a couple months of optimizations and blood, sweat, and tears, we're currently at like 2.9 seconds per region. It's close to 353 chunks per second. Now it takes 45 minutes to pre-generate a world, which is more than twice as fast. So we can get through all of our pre-generation in approximately 3 hours compared to 8. Yeah. It's approximately 2.5. Let's see. Yes, so the optimization process that I used to get this improvement was, if you really distill it down, it's just 3 things. I profiled extensively. I made 1 or 2 changes per round, and then I just kept repeating. And you can also use this process to work on anything, really. You just need to make sure to profile and then make your changes and then keep repeating to really let those optimizations compound and get all the benefits. So I'm going to be detailing what I did in each step. So For those who are unaware, profiling is a tool, a method you can use to gather data about which methods in your program are slow and figure out which methods you need to optimize. So there's a few examples of profilers that you can use. For beginners, I recommend Java Flight Recorder, as it's is really easy to figure out what it's doing, and it provides a wealth of information. And I found that if you don't understand something, you can just look it up. So it's really good. I personally use YourKit because it has a lot of really in-depth performance testing tools and such, but it is a paid tool. So that is the one caveat there. Yes, the Spark profiler is good, but I think you can't use that outside of Minecraft. Correct me if I'm wrong. Yeah. Spark is like fundamentally kind of similar to Visual VM. So if that's something that you're familiar with, it'll provide results that are similar to that. The one caveat that I would like to say with Visual VM is that since it kind of just traces the Java code, it has certain issues with safe point bias because the JVM inserts certain safe points where certain actions like garbage collection can happen, and Visual VM has a record, from my experience at least, with creating a lot of bias at those safe point regions. This can be mitigated with a Java flag if you disable safe points with experimental JVM settings. And Java Flight Recorder also suffers this to a certain degree. But yeah, I just wanted to say that. All right, let's keep going. See if next slide takes more than 5 seconds to load. Okay, yeah. Here's an example of a flame graph. I'm really sorry, this image is stretched. Yeah, it's a flame graph showing which methods are really hot in a certain piece of code. This is a flame graph of Quilt Flower, actually. It's what I was working on. Yep, good job. Yeah, so you can see that, like, as you go down, certain methods are wider. So that will tell you that those methods take longer to execute. So you know that if you want to start optimizing, you should probably start optimizing there. So step 2 of the 3-step optimization process is to use the data you collect from your profiler to make changes to your code. Because you need to profile to know which changes to make. And in my case, the longest time was base chunk generation. So generating the noise and converting that into a air, stone, and water world. And ore generation, because there are a lot of ores in Minecraft, because all the granites, andesite diorite blobs are also considered ores. And there's like 30 of those per chunk. So if you're generating 124 chunks, 1,024 chunks, there are a lot of ores. And yeah, let's now look at some methods you can use to optimize. And yeah, before we get there, we want to also understand what's so slow, why is it taking so long? And answering these questions is an important step in the process. because it'll help you understand what you need to do, and it's kind of important. So, haha, multi-threading. We've gotten here. So, multi-threading is really useful if you have a big task that is able to be split into multiple smaller tasks, aka it's pure and it doesn't modify any sort of like shared state. And I found that the fork join pool API is really good for making tasks that can split and utilize all the threads to its fullest potential. So essentially, I've gotten to the point where pretty much every single part of the world generator is multi-threaded by using certain things like for example, feature decoration, which is where all the trees, ores, and rocks and such are placed. It needs a 3x3 chunk radius around it to fully have all the context. So it's not possible to modify those chunks while it's being read. So a trick that I made was to split the 1024 chunks into a grid of 3x3 chunks, and so then it multi-threads the processing of like the same index in each grid, because if you do it that way, then the amount of chunks being read and written to don't overlap. And I'm really sorry that there isn't a slide for this, but I can make a diagram later to really show what's going on there. But moving on from multi-threading. Algorithmic improvements. Because in the case of like ore generation, the way it works is that there's a list of blobs with position and sizes, and those blobs are then placed into the world, but it's not really possible to multi-thread that. Yes, you did hear a rooster. Okay, we're just not gonna talk about that. We're just gonna keep going. Yeah, it's not really possible to, oh my god. It's not really possible to multi-thread this. So, what I had to do instead was to change the algorithm a little bit. Yeah, it is in the morning. I woke up at like 8:30 to get this talk in. Okay, yeah. First thing I did was to limit the ores spawning behind the air, because you can't really place ores in air. So if an ore blob tries to place in the air, it's just not going to place the blob, because there's a good chance that it's not gonna touch any stone. And I also found blobs in the array that are too small, so it wouldn't place any ores, and I just removed those so it doesn't have to perform the 6 nested for loops that Minecraft ore generation uses. Because when you're doing that at scale, it takes quite a while to go through all those 6 nested for loops, so it's better to just remove those. before iteration. Yeah. Or generation, yay. I think it's just 6. It might be 7. And final step of this process is to repeat this profiling changes loop and just keep finding things and making optimizations, because as you keep making optimizations, even if they're small, they will compound, and that's how it can really start making your application faster. Is it moving?
It's
Okay.
moving.
Yeah. Where are we now? We've optimized the Java code as much as it can go. We added multi-threading and we improved the algorithms. Speed is 3.4, which as you can see is not 2.9. So where is that coming from? So is it moving?
You can assume it's been clicked when you click it.
Okay, that
So yes.
it clicked twice. That's really good. It missed the thing that I wanted to say.
Oops.
There. We need to go deeper. So you're on. Where are we now?
Okay, yes. Achievement get, we need to go deeper. Yeah, Java level optimization is good, but what if we wanted more?
Do you want me to do it?
Yeah, please.
Oh dear.
Okay. There.
Yeah, the next slide was JIT. I have
Yeah,
lag.
it's on. Yeah.
Server is having another hiccup.
Yeah, you've got 16 seconds of ping.
16 seconds. Yeah, that sounds about right, considering where I am.
You're on the JIT recap slide.
Yes, okay. So, just to recap, when you compile Java code, it's turned into bytecode by Java C. At runtime, depending on how often your code is run, the bytecode is either interpreted as is, or it's just in time compiled into assembly. And I'm gonna click the next slide button. It is my internet. Yeah, I know.
Yeah, you're on it. It's assembly.
Okay.
Went forward 3 times for me, I think.
Whoa.
For me, it's an overview.
Yes, assembly overview. By understanding the architecture of the CPU here, and oh my god, are we on the first slide or the? Okay, yeah, there we go. Yeah.
The first one.
By understanding the general architecture of CPUs, you can find a lot of potential for optimizations that you wouldn't really see just by using a Java level profiler. Yeah. I'm gonna actually pull up the PowerPoint locally. So,
Yeah, do.
yeah. Where was I? By understanding the general structure of CPUs, you can find a lot of different things that you wouldn't have known just by looking at the Java code. But just as a forewarning, everything after this point is it's kind of complicated. It really does feel like dark magic, and we're just continuing on for science. Yeah, let's go to the next slide.
Assembly level profilers.
Yes. So, to understand what your JITted code is doing, you can use some assembly level profilers like Intel VTune and AMD's microprofile to find which actual instructions of assembly code are slow and try to figure out ways to optimize that through Java. It is arcane, and I talked to a friend about it, and she said it was like speaking with an eldritch god. And yeah, that sums it up pretty well. But we're gonna keep going because I want that performance. I'm gonna get it. Next slide, please.
Yep.
No,
Use
those tools
multiply,
are
add
just
instructions.
straight up free. You can just download them. It depends on what CPU you have. Like, you can't use the Intel tool if you have a Ryzen CPU. I found that VTune has a much more user-friendly interface, but microprofile works pretty well as well, so it's okay. So we're going to talk about fused multiply add instructions. So as you can imagine, there are specific instructions for floating point addition and floating point multiplication. So so this talk is kind of focused mainly on, two slides are on x86 instructions because that is what my computer uses, so it was the easiest thing for me to look at and understand. You can do different things for CPUs that use ARM and such. So yes, fused multiply add instructions. On the Zen 2 CPU that I'm running right now, a multiplication instruction takes 3 clock cycles, and in addition also takes 3 clock cycles. But an FMA instruction takes 5 clock cycles, and it does an addition and a multiplication. So with that, you can shave off a singular clock cycle, which is it's slightly faster, but on certain cases like noise, it is really worth it. And so I wanted to talk about SIMD, which is a singular instruction multiple data, also known as vectorization, but I couldn't really find a good place to put it in this talk because the JIT compiler that Java uses isn't fantastic at auto-vectorizing Java code, especially if it has stuff like side effects. There's some JIT compilers like Azul's Falcon JIT that uses LLVM in the background. And but unfortunately that is a paid tool. So I do have some things that I want to talk about on the Java vector API that they're continually working on. It's in like its 5th preview or something, but it's not ready and they're still working on it. So I will save that for later. Yeah. All right. I think we should go to the next slide. I don't think it landed in 18 because they wanted to wait for the value types to land. Yeah. I did not say the AMD profiler doesn't work on Ryzen. I said the Intel profiler doesn't work on Ryzen. Yep, still waiting for Valhalla. Okay, anyway. So the few caveats about fused multiply add instructions and using them liberally is, as someone mentioned in chat, this is like spending 4 hours to get a like 1% performance improvement, and yeah, that's kind of true. And math.fma, it's good if you have fuse multiply add support, but if you don't have fuse multiply add support, because FMA is actually more precise than doing addition and multiplication, because it's doing the multiplication in the registers itself, which allows it to be more precise. To get the same precision on processors that don't have the instruction set, it has to emulate the instructions in just pure Java code, which is way, way slower. And what most modern processors, after Haswell on Intel and Piledriver on AMD, have FMA support. There are a lot of CPUs floating around that still don't. So it's something that you have to use with care. And the other caveat is like, you're shaving one singular cycle on modern CPUs. So unless you're writing noise gen code, this is likely to not do anything. But as we'll see, it did help me in my use case. Shall we go to the next slide? Yeah, I know the exact CPU model, so it's really easy to optimize for that CPU model. And the big thing actually is cache line optimization, because your CPU has multiple levels of caches, and accessing data from your L1 cache is something like, I don't know, 3 to like 8 clock cycles ish, just as a rough estimate to put things in perspective. But accessing data from your main memory is way slower, like in the hundreds of clock cycles. So what your CPU does, if it gathers one data from one memory location from main RAM, it'll move 64 bytes into your L1 cache or L2 cache at a time. So basically, if we can go to the next slide. If you ask for doubles 0, accessing doubles 1 through 7 will be much faster because the data is already in cache. So overall, this means that sequential reads out of an array are much faster than random reads. So something that I didn't realize when I was writing strided arrays is that you should access them linearly. Can we go to the next slide, please?
Yep.
So if you have an array that's in x times 16 plus z, for example, like if you wanted a 16 by 16 array but wanted to make it a single dimension, then your iteration should have x on the outside and z on the inside. So if you're traversing an entire chunk section worth of blocks in an array, for example, if you access it in the like index first, so accessing it linearly, it's actually quite a bit faster than accessing it non-linearly. So that's something that I wasn't aware of when I started writing this code. So it was a really simple change, but it had really massive performance implications. And if you're wondering if what to look out for if you need to know when this is a problem, you can look in microprofiler for L1 meshes. And those will have instructions that are reading data from cache from main memory, and it's not using the full potential of the L1 data. Can we move on to the next slide, please? Yep, thank you.
Inlining.
Yeah, inlining. The JIT compiler can inline hot methods that are less than 325 bytes of bytecode by default. So if it has a lot of smaller methods, it's able to kind of coalesce them into a much larger method and try to optimize that. And so when that happens, you can the JIT compiler is able to make better decisions on which loops can be unrolled, for example, and which values can be hoisted and which branches to elide, because it has the greater context of all of the methods that you're calling. And also, because calling a method is rather slow, you need to set up your stack frame, and you need to push all the values onto the stack, and you need to call the pointer to go to where the method is located in memory. So that is a lot of data that needs to be shuffled around to perform a method call. And so if it's inlined, it can skip all that overhead and also have a much better time optimizing your code. We can move on.
Got it.
So you can look at the inlining of your code by adding the print inlining JVM flag. It's best for performance if all of the methods labeled hot also are inline. So there's a specific string that the JVM says if it is not able to inline a hot method. It's harder to use a profiler to see inlines because to the profiler it's it doesn't really have the context of the JVM, so it doesn't know which methods have been inlined. So it's much easier to just use the print inlining tool. Oh my god, this freaking rooster. It's like right outside the window too. Okay, anyway, I'm really sorry. Yes, JIT watch is really good for viewing JIT logs. You have to make you have to add a few other JVM flags to get it to print out compiled code and such, but it's really useful. I found it as well. The rooster doesn't have a name. It's a neighbor's, I think. But anyway, let's keep going.
Yep.
Yeah, so we're nearing the end. So a lot of these pillars of optimization can be used for noise code, and it doesn't really make sense to redo the effort. So I spent about 2 weeks on this noise code to try to perform dark magic to get the JVM to like this the code. So you can view that in this GitHub repository. it has the optimized version of the original legacy open simplex noise and the new column open simplex noise. So compared to upstream, this has diffused multiply add instructions. It has everything inlined, and it aligns a few branches to try to get everything to be as smooth as possible. And in ideal cases, it's close to like 5 to 15% faster than upstream. So it's not a lot, but if you're doing a lot of noise, that extra performance boost can help in quite a lot. And big shout out to k.jpg, who is in the chat right now, who wrote the open simplex noise originally. So massive shout out and thank you. And compared to the FMA instruction set, emulating the FMA instructions in Java code is significantly slower, like way slower than you would imagine. And there's actually a few cases where using FMA is actually slower than not using FMA for reasons that that I honestly don't know either. On certain older Intel processors, I tested it and it was actually slower. So it's a thing for another day, but I will keep you all updated if I find something about that. So it just goes to show that all of this has caveats and you need to use it with nuance. It's not just like, oh, I'm gonna replace all my multiplies and adds with FMA and it's gonna be magically faster, because there's a good chance that it might not be. Let's move on. And that's supposed to say 2.9. I typoed. And at the end, we're now at the 2.9 seconds per region that I said before. Getting here was not easy in the slightest, and took months and months of like blood, sweat, and tears and effort. But I'm really glad that I did this because I learned a lot about how CPUs work, and it really helped me have a deeper understanding and appreciation for what the JVM does, because it is magic, y'all. And I think that's it. Is there a next slide? That should be the question slide, I think. Oh, right. If y'all found any of this interesting, and you would like to see a presentation that is slightly better, well put together, I have linked 4 different talks here that talk about different things they can do for optimization and to understand what the JVM is doing. I'm gonna upload this PowerPoint somewhere when I'm done, probably Twitter. So you can click on these links and enjoy. I think the questions and answers slide was on the front, but it's okay. My Twitter is not 18+. I think I'm gonna open questions, so if anyone has questions, feel free to write it in the book or just ask in the text chat and I will try to answer it. Oh, that is a lot of questions. Okay. Have I touched a project called Wave Function Collapse, and have I used it to generate structures? I've heard of wave function collapse, and it's really interesting, but I haven't had a chance to look into it very deeply yet. In my personal projects, I've been trying to make new ways of generating structures that aren't just the general build a town center and then iterate outwards. But it's just been something that I've been working on and off, and haven't really had any results to show just yet. How is 1.19 treating you? Haha, I am not going to talk about 1.19. It doesn't exist, and 1.19 is fake. To use JIT hints, you need to know the CPU architecture, but how do you get that? So the easiest way, actually, is to just look at the CPU that you have and try to find the data sheet for it, because Intel and AMD provide both optimization guides and block diagrams for how your CPU works. And there's a few resources, such as there's a website called uops.info and Agner Fogg's optimization tables that are really useful for finding out the specific latencies of each instruction. Oh, dynamically. That is something I've thought of, because I wanted to make it so that the FMA instruction with math.fma was automatically replaced with a times b plus c if your CPU doesn't support FMA. But the problem is that then you would need to call the CPU ID instruction from Java code, so you'd need J and I there, and that just seems kind of like a massive pain in the butt. So it's not something that I've looked into just yet. How are you lighting a chunk/region? I'm not. I'm just doing it. So the Origin Realms chunk generator is fully divorced from Minecraft. So it just hands over the chunk data, and when the chunks are first loaded, it does all the lighting because it's set at the feature's chunk status. How often does using math.fma gain performance over just letting the JIT find cases and create FMA instructions? So, that's kind of a tricky question, because I found in most cases that the JIT doesn't really produce FMA instructions, because there's accuracy implications. So generally all FMA is done manually. Is there a way to set up quick and repeatable tests for biome generation? Unfortunately, that's kind of tricky, because biome generation, you need the code from Minecraft. So in my case, it's better because everything doesn't depend on Minecraft. I can just make a new main class and run the biome generation there. But you may have to figure out something there, unfortunately. I don't really have any tips, fortunately. How many cores/threads does the server running these benchmarks have? Which benchmarks are you talking about? Oh, the seconds per region. It's a Coffee Lake processor, and I think the container has 6 threads. how did I get started profiling Worldgen like this? Mainly because the 8 seconds per region was abysmal, and we really needed to figure something out to get it faster. And I've always kind of had an interest in optimization, so it was really fun getting to the low level and figuring out what everything does. What is my favorite x86 instructions and why is it? Let's see, p compare x string x. Yes, that is my favorite x86 instruction. I think the other x86 instruction that's my favorite is the one that creates an interrupt everywhere, and it's really funny because in AMD's official instruction like timings spreadsheet, it has a timing of something like 56,000 clock cycles, and it's just really funny to see the clock cycles go from 1 instructions per clock, or 3 clocks per instruction, and then just going 56,000. I think that was the number. Will there be a quote Worldgen API to make working with generated structures, biomes, and other Worldgen stuff easier? I don't work on the Worldgen API, so unfortunately I do not have answers there. Have I considered GPU acceleration for world generation? I have considered it, and I didn't do it, mainly because at the amount of noise that I'm generating, the PCIe bandwidth between the CPU and the GPU is likely going to be the limiting factor. That's not really anything that I can change. So it's easier just to use fork join pool and multi-thread it to hell instead of trying to force the GPU to generate the noise. My laptop is about to die. Let's see if I can get through these last 2 questions. How am I saving the region files? We've noticed that saving is a big bottleneck, mostly due to NBT object allocations. The saving is, so when it kind of just saves each chunk with an optimized version of chunk serializer, I think. I haven't looked at the saving code that much because I didn't write it. So I think that's it. I can ask and get back to you on that crop. In my opinion, what's the best free JVM profiler? I think the best free JVM profiler has to be Java Flight Recorder, just because it gives such a wealth of information, and it's free, and it's really easy to get started with, and there's a lot of tutorials online. And I think that's it. That's all the questions for today. I'm really glad people were interested. Oh, Java Flight Recorder, JFR. What does it feel like to be a Worldgen modder and having everything break every version? Pain and burnout.